Number 1, find the force statement regarding power. Power is work per time, and differential of work is force scalar product displacement. If I divide this one with dt, then it becomes force times velocity. It's scalar product. That's correct. In classical mechanics, it means it is Newtonian mechanics. The mass m of a particle is invariant. It doesn't change. But in relativity, we'll see at the end of this class, the mass varies depending on the velocity if we consider the Einstein's relativity. However, if we can ignore the velocity dependence of mass, then force is just the mass times acceleration. So this m dot equals 0 in Newtonian mechanics. Power can be expressed as a force times velocity. So this is a force times velocity. And it is just a time derivative of kinetic energy. Okay, this is the same. If I just multiply dt in here, this one cancels and it becomes total differential, but 1/2 is missing in here. So this one appears repeatedly. So this can be applied to integration by parts. This factor 2 is missing in here. Scalar product, it can be expanded in terms of Cartesian coordinates, and then we take the differential, so first one and second one, and it becomes a dA dot product B plus A dot product dB. Triple scalar product differential, we have 3 factors. So first differential, second differential, and third one differential. And sum of them is the answer. Number 3, uniform circular motion. So angular velocity is perpendicular to the plane, xy plane, and omega dot equals 0. So uniform circular motion, omega is constant. The position vector of an object can always expressed as in terms of radius and unit radial vector, right? And ER, this one rotates. This is a E1 and this is E2, and ER makes an angle of theta, and that this theta equals omega t. So radius, unit radial vector is a cosine sign, and unit tangent vector is this one is replaced with minus sign. This one becomes a cosine. X dot is the same as omega cross x. Let's see. RER hat is x. So omega cross x equals omega E3 cross ER hat R. So omega R, 3 times R equals theta, right? So this is the same as R omega e to the is theta. Okay. What is the force? Force is omega cross omega cross r, this one. And omega cross r is x dot in here. So we can substitute in here. The answer is the same, always toward the center. And angular acceleration is, radial acceleration is r omega squared minus er hat, right? Power of the particle is 0. The reason is that f dot dx is the work, differential of work, and f equals toward the center, and this is er and e theta, they are perpendicular. So this is not a vector. Therefore, dw equals 0 always. The reason is that the force is perpendicular to the displacement always. So this work is 0. If I divide it by time differential, it becomes power. Power is always 0. Power is 0 means kinetic energy. Kinetic energy is conserved. We have the same, its velocity changes, but its speed is the same, and its kinetic energy is constant. Uniform circular motion. Number 4. Find the false statement regarding kinetic energy. Newton and Descartes, they did not know. Although they are very famous, they were ignorant of the energy. Energy concept has been developed very, very late. You know, the Leibniz and Newton, they are of the similar stage. They lived at the same time. But Leibniz understood energy first, and he called it bis viva. Unfortunately, Leibniz made a mistake, 1/2. This 1/2 factor missing in his kinetic energy. He did not introduce the word energy. So, however, origin of the energy comes from Leibniz. He's a very important person. And then later that, Émilie du Châtelet is a French physicist, and she translated Newton's Principia into French. And she is the first person who developed the kinetic energy, idea of kinetic energy. And today what we learn is Coriolis work kinetic energy theorem. In addition, you have famous Euler. Euler is who made this number E. Euler and Lagrange. They developed the concept of energy very deeply. So Lagrange developed Newtonian mechanics into a different level. That is called the Euler-Lagrange equation. So they knew very well about energy. And very recently, about 130 years ago, Hamilton appeared. Hamilton developed a very basic idea, what we learn today, total mechanical energy. What we learn from now on will be mainly on the total mechanical energy conservation in conservative force. And concept of total mechanical energy was well established. He is very well behind all of them. But using this idea, total mechanical energy is actually we call in classical mechanics a Hamiltonian, named after his a very important person who developed the idea of least action principle. You do not have to know very well right now, but anyway, Lagrange, Hamilton, they are well acquainted with the concept of energy, and we are indebted for current formulation of classical mechanics to Hamilton and Lagrange. And all the development was made by Leibniz and Chatelet, and the word kinetic energy that we learn today was constructed by Coriolis, who is very famous for the Coriolis force. Five, sometimes later in this semester, T will appear as a temperature, but for the time being, I will write capital T for the kinetic energy. Kinetic energy can be written in terms of 1/2 velocity squared, or because mx dot is the linear momentum p, I can factor this out as a p squared over 2m. In either form, this is the form that Lagrange like. This is the form that Hamilton like. So kinetic energy is either this or this. They are the same. The time derivative of the kinetic energy, if I take the derivative, then 2p dot p over 2m, 2 cancels, and p dot is the force, and this is mv divided by m. So cancel, aha, F scalar product velocity. This is power. Actually, this is the origin of work kinetic energy theorem. The kinetic energy's time derivative is just nothing but power. That is the work kinetic energy theorem developed by Coriolis. P dot, time derivative of linear momentum, is a force. Okay. T dot, this is power. Power multiplied by time differential. That is the dW. dW is F dot dx. So this is wrong. Find the fourth statement regarding dimensions. Kinetic energy. Energy is force times displacement. Force is a mass. Acceleration is length divided by time squared, and distance length. So m length squared time minus 2. This is correct. Force has the dimension of a force. This is a force, mass, length. Length time squared. Okay. Power. Power is a work divided by time. So use this divided by time. Everything the same. One more time. So it becomes a minus 3. That's correct. Velocity, length divided by time. This is wrong, right? Find the false statement regarding the units. SI unit of kinetic energy, any kind of energy, is a joule. It looks okay, but it's wrong because I have to write in this style. It's a Roman. Any unit, any physical unit must be written in Roman. It is italic. Any italic letter must represent a physical variable. Physical variable. For example, mass, m, f, they are all italic. F equals ma, so italic. But meter, it should be in Roman. Okay? Units of power is joule per second. That can also be written as a watt. SI unit of work is joule. So this is wrong because it is italic. It should be right. It is a Roman. SI unit of force is Newton. Newton is a mass acceleration. So SI in SI unit, kilogram meter per second square is Newton. 8. We are familiar with this problem, and at t equals 0, it was a stationary, and this one, capital M, is greater than small m, so it will accelerate in this direction. Capital M accelerates downward, small m accelerates upward. That's correct. Both capital M and small m accelerate with the magnitude, so we have total mass times acceleration is the difference of the forces. If I simplify this one into a one-dimensional problem, so we have some capital mg is applied to this direction, small mg is applied to this direction. The difference of the total force will be like that, small m, so capital M minus small m g. We know the acceleration is this. That's correct. X varies from 0 to h. X varies from 0 to h, goes down. The kinetic energy increases. Work kinetic energy theorem states that the kinetic energy change is due to the force, net force, times displacement, right? So from here to there, we have displacement by h, and we know the acceleration. We know the acceleration. So this acceleration gives net force, capital M, A, and then multiplied by h. This is the amount of work done on the capital M. So let us substitute this acceleration, this m minus m over m minus m plus m, g, h. This is the answer. That's correct. As y varies from 2h to h. So 2h to h. So it is going up. It is going up. The kinetic energy increases by mgh. That's wrong. We have to use this kind of formula. It should be replaced with the small m. acceleration is the same and the same direct along the same direction, it makes a displacement small m a h. That is a small m. This is the work done on this small m. Okay. 9. Particle of mass m. We are also familiar with this problem. So constraint force exerted by the circle to the particle does not work at any time interval. Constraint force is in here. Constraint force is a normal force, and that is always a perpendicular. Normal force, either up or down, is always a perpendicular to the motion of the particle. Therefore, constraint force never carries out any work. The constant force exerted by the circle to the particle is always perpendicular to the differential displacement. That's correct. The kinetic energies of the particle at C and A are always the same. In here, because the constraint force does not work, and the only remaining force is a gravitational force. And gravitational force is, we will learn that it is conservative. Work done by a gravitational force is depending on the difference of height. And these two points are of the same height. Therefore, there is no change in the displacement as long as F equals mg times some displacement, and there is no displacement. Sure, there is a horizontal displacement. That horizontal displacement is perpendicular to the gravitational force. The only contribution of the displacement is for the parallel component to the gravitational force. So A and C are all has the same kinetic energy always. The kinetic energy of particle B is greater than. It is slower. When you climb up, it slows down. It's wrong. Number 10. This is just straightforward calculation, but you should be familiar with this kind of exponential, sine, cosine, taking the derivative or taking the evaluate the integral. Let me introduce a little bit unfamiliar one, but we are now well acquainted with the e to the x, e to the y, or sometimes we have introduced e to the I theta. Okay, and we already know that e to the I theta equals cosine plus I sine theta. So this complex representation has cosine, either cosine or sine in the real part or imaginary part. In real world, it is unnecessary to introduce the complex variable. However, introducing a complex variable greatly simplify your calculation. So it is for our convenience. We have a variable that is only defined in the real variable. In here, we have complex variable. It looks complicated, but the result is always much simpler than the case when we stick to the real variable. That's the reason why from now on, I would go back and forth in real space or complex space. We call the extension of this real variable to a complex variable as long as it is differentiable. In complex analysis, differentiable is called another name, analytic. And if it is a differentiable function everywhere, that example is exponential. Exponential function is a very convenient function, and it is differentiable everywhere on the real axis as well as all complex plane x plus iy. If you admit the fact this exponential function is defined both in real variable and complex variable, we simply extend the region from real variable to whole complex plane. So, for example, this exponential function is an entire function. Okay? Entire function is differentiable not only along the x-axis. What we know is e to the x, the derivative of e to the x itself along the real axis, but it is true for any complex number. In that case, what we evaluate that has a very complicated structure of cosine exponential or sine to the nth power exponential or something like that. These kind of thing. It is very tedious to derive the real variable formula. However, if you make use of this complex variable and then take the real or imaginary part, you finally end up with the complicated formula by extracting very simple formula by taking the real or imaginary part of this expression. This is a very important trick that we will face frequently until the end of this year. Even in the next semester, if you are not acquainted with the complex variable, you have to work very hard by carrying out tedious calculation. This expression and this expression are equivalent. However, derivation from here to there is quite straightforward. However, derivation from this to there is very complicated. So I would like to let you be familiar with this complex variable analysis. It's not a serious problem. Okay, in short, everybody knows this integration very well, but if you want to carry out this cosine or sine structure, this integration, what you want to do is just to replace this one as exponential integral, because cosine is e to the cosine bt equals e to the bt or minus I bt cosine real part. This is a cosine bt. And this is a real. Therefore, the real part of this integral reproduces this cosine times exponential function integral. In a similar manner, imaginary part of e to the minus I bt equals minus sine bt. Using this fact, minus imaginary part of this one is the same as this. However, we can make an analytic continuation. You know the formula for the real variable function. Just to replace this real number a with A plus IB. Both of them are real, but A plus IB is a complex number. This is true. And your calculation becomes very, very simple. Okay. Number 11. We have a damping force that has coefficient B that is positive. Minus x dot means the force is opposite to the velocity. So in that case, F dot x dot, this is minus bx dot squared. This is a negative definite as long as the particle is moving. Because of this, the power is always negative. That means according to the work kinetic energy theorem, the kinetic energy of the particle decreases. The kinetic energy of the particle decreases because of the damping force. Very, very important. Okay. Now, let us substitute m acceleration to the net force. If this one is the only force, then equation of motion becomes like that. As I already told you, we can replace this one x dot with v, then equals mv dot plus bv equals 0, and the variable can be separated in this case. And as is written in here, we can make the integral for the velocity and integral for the time separately. And this differential equation, this equation of motion is completely integrable, and just a simple one-dimensional integral will give the answer. At t equals to 0, if we substitute t equals 0, x dot equals a v that reproduces the initial state condition. We have this equation of motion, and we multiply x dot both sides. Right hand side is still 0, and then we simplify this one. This one is the total differential of kinetic energy. This is a time derivative of kinetic energy. And the factor 2 is missing. That's the reason why the answer is a C. 2 is missing, so this is wrong. Change in kinetic energy during the time interval 0 to t is just because this is the kinetic energy. If you integrate this one, you will find the left-hand side, the delta kinetic energy, because this is a kinetic energy. And then right-hand side is a minus bx dot squared time. So if you carry out this integral, you will find the lost amount of kinetic energy. And you know the solution in here. Substitute this one in here, then it is an exponential function, and you know the answer. You know the answer. Using this integral table, we find that this one is 1 at t equals 0, and decreases smaller than 1. So this is this amount. This amount in the brackets is a positive, and we have negative sign, so kinetic energy decreases. In the limit t goes to infinity, as t goes to infinity, this one vanishes, this is 0, that means the whole amount of kinetic energy is lost. At that time, the system makes a complete stop. X dot equals 0. Number 12. Equation of motion for particle under net force is this. Newton's second law. Multiply dx in here. That's fine. This is the work done by this force during the infinitesimal displacement dx. And then we substitute x equals m in here. And then this is the derivative, time derivative of velocity. And then we change the variable from x variable to time, to velocity. So it becomes velocity, and this is a velocity is a differential. So this one becomes a velocity, and then we have velocities differential in here, and m is momentum multiplied by acceleration, that the differential of the velocity. Finally, this one is expressed as total differential of the kinetic energy. 13, this is an equation of motion for simple harmonic oscillator. The simple harmonic oscillator accepts a force that is minus kx, because this is F. If I move this one to the right hand side, the net force applied to this system is a minus kx, and this one means k is a positive, and this indicates that force is toward the origin. If there is a displacement by x, the force is opposite. If it makes a displacement to the negative sense, the force is a positive, something like that. So always opposite to the displacement. The change in the kinetic energy from 1 to 2 can be computed by force. And this is nothing but the work. This is a work kinetic energy theorem. Change in kinetic energy from x1 and can be computed. F dx and F minus kx is substituted because this one indicates the force is minus kx. All right. The third one, this one is minus kx. Minus is missing. This one is wrong. This is, you don't have to derive completely. In the next semester, we will study the Einstein's special theory of relativity. But this is just let us read it through. Both the classical mechanics and relativity. Classical mechanics is it is a Newtonian mechanics, and Einstein's relativity. Force is expressed. Okay, that's right. Very important. Linear momentum, time derivative is a force. This is correct both in Newtonian and Einstein's relativity. If a particle has a speed that is not negligible in comparison with the speed of light, the mass must be written as in this form. Because of this, m dot equals non-zero. So F equals ma. This is true only for Newtonian. This is wrong in relativity, remember. However, this one is correct in both relativity and Newtonian mechanics. Just memorize. You don't have to understand it. That is a fact. Just memorize. The linear momentum of particle is a mass times velocity. That's correct. However, this mass is depending on the velocity. That's the difference between the Newtonian mechanics and Einstein's relativity. F equals ma valid for both? No, it is valid only in the Newtonian mechanics. This is wrong in relativity. In relativity, this is correct. Momentum divided by the time derivative of linear momentum. And linear momentum is mass times velocity. That's fine. However, this mass varies depending on the velocity. And any object cannot have the velocity greater than the speed of light. The only particle that can travel with the speed of light is photon, electromagnetic wave. That is the only any massless particle can travel with the speed of light. And anyway, in that region, in that regime, the Newtonian mechanics completely break down. 15, you don't have to understand, you just memorize. In physics and mathematics, there are Greek letters appear so frequently, and you know the very famous Omicron. Omicron is O. There's a Greek letter. Delta, you should be familiar with this capital delta and small delta. This is a capital gamma and small gamma. Epsilon appears in two different waves. And this is zeta, this is eta, this is a small theta, and this is a capital theta. And in English K, then Greek letter K is a kappa. And wavelengths, we use usually lambda, and capital lambda is written in here. And mu, just like M, nu, just like N, appears in here. And the Xi, small Xi, and large Xi. And pi, you're familiar with the 3.14, this pi. And capital pi appears in here. When we express the multi-product, we usually use capital pi. As a rho, that is a density or something like that, we use the rho because it is a ratio R. So rho. And T is tau. Sigma for standard deviation, and sigma, capital sigma, is for summation notation. This is Y. Upsilon represents a Y. And this is a small upsilon. It looks like a V, right? But it is a Y actually. And phi, especially used for azimuthal angle, capital phi. And chi and psi, usually used for the wave function or psychology, capital psi. And omega is the last word, alpha and omega, and this omega is the last, the Greek alphabet. 16, we find a false statement regarding the equation of motion, simple harmonic oscillator. We have some displacement, the origin, and initially the mass spring system is in here, and it accelerates toward this direction, and then until the time it reaches the maximum position. And you will find this system is symmetric. It's a minus x0 is in here, and it again stops at x equals plus x0. Anyway, we know the total differential. Using this by multiplying the velocity, we can find the total differential of kinetic energy. This is the total differential of the kinetic energy. This is the total differential of, we will learn it later as a potential energy. And this is the kinetic energy. Because the differential sum is always 0, this one indicates that differential of this sum is 0. That means that this is a conserved quantity. Conserved quantity. If it is conservative, then it doesn't change with respect to time. Therefore, we can make use of a single value evaluated at a certain time. You don't have to repeat the calculation. That's the right reason why we learn this conservative force. All right, because this differential is the same, why don't we write this x dot squared plus 1/2 kx squared equals a constant. If it is constant, then what happens in the initial state? In the initial state, velocity was 0 and position was x0. So because it is constant, velocity was 0, so 0 plus 1/2 kx0 squared. We have this very simple identity. From this identity, I can find out the kinetic energy of this particle at any position. If we move this one to the right hand side, then is 1/2 k x0 squared minus x squared. Now we change the variable. We introduced xc. xc is x over x0, the single variable. In that case, it becomes 1, and vector 2 cancels, and mass is divided, so we have k over m and 1 minus c squared. And this part and this part, let's see, what is that? C dot equals time derivative of c, right? So time derivative of c is a constant, and that is always a positive. Then what happens? C over dt is square root of k over m, 1 minus c squared. Why don't we divide this one both sides and multiply dt both sides? Then now we end up with this complicated equation into a simple integral. Now we can integrate over c and integrate over time very simply. And now we already familiar with this integral. This is the arc sine. Arc sine is an inverse function of a sine. So from -1 to 1, -1, what is -1? C equals a -1 means x equals minus x0. So c equals a +1 means x equals a plus x0. I told you we began with the system initially at rest at x equals x minus x0, and it accelerates, and then when it passed the origin, the force is backwards, so it slows down, and at the end of the day, you will find that this one stops in opposite position. X dot becomes 0 again. So I'd like to find the time from in here to there. And this integral is arc sine. You know, this is a sine theta approaches 1 at half of pi. This is sine theta. So it is inverse function is something like that. And it approaches half a pi, and the value at xc equals 1. And in here, c equals -1. Our starting point in here, starting point to end point. So at starting point, its Einstein value is minus half a pi. So finally, from this expression, we can determine the period of this oscillation. From in here to there, it is just a period of half. And due to the symmetry, when it makes a round trip, it takes 1/2 of time, t period. So sum of this will be total period, and this period is completely determined from this integral of arc sine. 17. Now you should be familiar with these integrals, and these integrals, this derivative, and then this formula can be used to find the integral. And what I want to tell you is how to derive the binomial expansion. 1 plus x to the alpha, and alpha, whatever alpha is. However, x should be in the region 0 to 1. In that case, it is you repeat the derivative because of this formula. For example, if I take the derivative of x squared, we have 2x. That's fine. But what happens if I have 1/2? There is a square root of x. Still, we have 1/2 x, 1/2 minus 1. This rule, x to the n's derivative is n, x to the n, is true for positive integers. However, it is also true for any real number. That's the important point, because now you know how to take the derivative of exponential function. So finally, you have the derivative of this, and if you repeat the derivative, what you get is first order derivative is this, the second order derivative is this, and third order derivative is this, and so on. So now you can find derivatives at x equals 0. So we can make a Taylor series expansion of this binomial expansion. That gives at x equals 1. For example, it is because it is 1 plus x, and when I substitute x equals 0, it is evaluated 1. So it's better to write alpha minus 1, alpha minus 2, alpha minus 1, and so on. And then substitute y equals 1 plus x, and take the limit x goes to 0. So we finally find the binomial expansion. We do not want to reproduce any detail about the higher order power. For small x, we usually are interested in the first few terms. That's quite important in the expansion formula. Okay, so now you are able to evaluate the square root functions integral. This can also be extended to the change of variable to find a trivial extension. And we apply in the non-relativistic limit the Newtonian mechanics holds the kinetic energy can be evaluated by evaluating the work done by the force times displacement. And the final result was the kinetic energy, right? However, in relativity, we just learn that mass is like that, force is like that. So we substitute these to find the kinetic energy. Force, this works even in relativity and displacement. And in here, you can follow this calculation using the formulas that we have already derived. Finally, let me just tell you the final result is. This is the kinetic energy of relativity. And here you will find mc squared subtracted by m0c squared. And in here, m0 is the rest mass. Rest mass is not a remnant, but a particle's mass when it is not moving. And this m is a particle's mass when it is moving. And this difference is quite large. And in the limit, the speed of particle approaches the speed of light, it can grow to infinity. In addition, this subtraction means any object with the rest mass m0 and standing alone do not move, and if this mass disappears, we have enormous amount of energy. This enormous amount of energy, after losing its own mass, it produces an enormous amount of energy that we are using, and in some cases it is badly used to kill people. So nuclear energy comes from this mass energy. Finally, when we make a differential, the finite change in a function varying a variable x by a finite amount, according to Taylor series expansion, we find it is a sum of various terms as expanded as a power series. However, as the delta goes to 0, this one all disappears. That is well explained in this expression. We are well acquainted with the definition of Euler's number, but what happens to the case if I add 1 over n squared, something like that? That is equivalent to include the higher order pieces. However, in the limit n goes to infinity, this kind of pieces disappears completely at the end of the day. So that's the reason why we keep using this very simple formula developed by Euler. And because everything is already completely solved, just you follow how to reproduce these results. Okay, that's it for today.